Students, welcome to Sunil's tutorial. I'm Sunil Bhivani and today we'll be doing this chapter called as stationary waves. Let's see this. What do we understand by free vibrations? What is the meaning of free vibrations? Now, when a body is capable of vibrating when displaced from an equilibrium position and release, it begins to vibrate and due to the restoring force. Suppose if I have a body, this is the mean position, it has been displaced from the mean position and has been released. If it has been displaced from the mean position and if it has been released, it will start moving towards the mean position. Due to the restoring force, it will move to the other side, come back, right? Now in this case, when a body capable of vibrating is displaced from the equilibrium position, this is your equilibrium position, and released, it begins to vibrate due to the restoring forces acting on it. The vibration of this body is said to be free vibration, right? So what is free vibration? And the frequency with which it vibrates is called as natural frequency. So free vibrations therefore can be defined as vibrations of a body where the body vibrates with its own natural frequency when it is left free. I release the body and leave it free, so it is going to vibrate with its own natural frequency and without any external forces acting on it. That is called as free vibration. The frequency with which the body will freely vibrate is called as the natural frequency. Fine. So I can say a body capable of vibrations, a body capable of vibrations when displaced from its equilibrium position, when displaced from its equilibrium position and released, begins to vibrate due to restoring force, begins to vibrate due to restoring force, right? Now in this case I can say that the vibration of the body, this vibration of the body in this case is called as free vibration. Vibration of the body in this case is called as free vibrations, right? The vibration of the body in this case is called as free vibration, and the frequency of vibration of the body is called as natural frequency, and the frequency of vibration of the body is called natural frequency, right? So in that case, how would I define free vibration? First let's define natural frequency. How would I define natural frequency? The frequency with which a body vibrates freely, the frequency with which a body vibrates freely, the frequency with which a body vibrates freely at its own or on its own is called as natural frequency. Right? In that case, how do I define free vibration? Free vibration. Right? Free vibration. The free vibrations can be defined as the vibrations in which can be defined as the vibrations in which the body vibrates with its own natural frequency. The body vibrates with its own natural frequency. Fine, do we get this thing clear? So that is free vibration. Once we know what is free vibration, let's try to understand what is forced vibration. Now, if some external periodic force is constantly applied to the body, then the body continues to vibrate under the influence of external forces. Such a vibration is called as forced vibration. Mean position, displaced, right? Now, if I want to constantly apply some force here, the body vibrates, goes, comes back, I again apply that force. Periodically, I keep on applying external force, external constant force. Then the body will not be vibrating with its own frequency, but will vibrate depending upon the frequency with which I am applying the external constant force, and that vibration will be called as forced vibration. Right? So what is forced vibration? If some external periodic force is constantly applied to the body, if some external periodic force is constantly applied to the body continues to vibrate under the influence. The body continues to vibrate under the influence of such external force. Right? So in this case, such vibrations of the body are called as forced vibration. Such vibrations of the body are called as forced vibration. Right? So how do I define forced vibration? Forced vibration can be defined as the vibrations in which the body vibrates with a frequency, other than the natural frequency, under the action of some external periodic force. Under the action of some external periodic force. Right? That is called as forced vibration. Right? Next, the amplitude of the forced vibration depends upon the difference between the natural frequency and the frequency of the external periodic force. The body is going to vibrate with its own natural frequency. I am applying some external periodic force. Now what will be the amplitude with which the body will vibrate will depend upon the difference between the two. The amplitude would be large if the difference between the frequency is small, right? So suppose let's assume that the frequency of the applied force gradually increases from smaller value. then the amplitude of the vibrating frequency will also go on increasing. When the frequency, that means when the applied frequency or when the applied force becomes equal to the frequency of the body, then the body will vibrate with maximum frequency, because the difference between the frequency will become zero, and at that point the body is said to have resonance. Right? So what is resonance? If the frequency of the applied force is equal, or if the difference between the frequency of the applied force and the natural force is zero, then the body the body vibrates with maximum amplitude, and that is called as resonance. Resonance. Body vibrating with some natural frequency. The body is vibrating with some natural frequency. Right? Say, let's assume that N0 is the natural frequency. Let's assume that there's some external periodic force applied, right? The external periodic force frequency is, this is the frequency that is applied to it. Now, what amplitude it will vibrate with will depend upon the difference between these frequencies. If the difference between these frequencies is small, then it will vibrate with maximum amplitude. If the difference between these frequencies becomes zero, it will vibrate with maximum amplitude, and that is called as resonance. So when the difference between the applied frequency and the natural frequency becomes zero, the body starts vibrating with maximum amplitude, and such a condition is called as resonance. Fine, do you get this thing clear? What is resonance? So what is resonance? I can say that the phenomena of making a body, definition, the phenomena of making a body vibrate, making a body vibrate with its natural frequency the phenomenon of making a body vibrate with its natural frequency under the influence of external periodic force, under the influence of external periodic force, is called force of frequency equal to the natural frequency of the body is called as resonance. Right? I can say that in this case the body vibrates with maximum amplitude. The body vibrates with maximum amplitude of forced vibrations. So do we understand resonance? Resonance is a phenomenon under which the body is made to vibrate at natural frequency due to some external force. Right? Okay. Now, let's try to see the resonance curve. Let's consider that this be the driving frequency. And let's consider amplitude on y-axis. Right? In that case, the resonance curve would be like this. this frequency, the amplitude would be maximum at frequency n0, which would be the natural frequency, and at this point the amplitude will also be the maximum amplitude would be, say, A max. Right? That's how your resonance curve would look like. So the variation of amplitude of force vibration with frequency of the applied force is called as the resonance curve. This is your resonance curve. Resonance curve. What is resonance curve? The variation of amplitude. Yeah, this is your variation of amplitude of forced vibrations. The variation of amplitude of forced vibration with frequency, the driving frequency is on x-axis, with frequency under the influence of the variation of amplitude of forced vibration with frequency of applied force is called resonance curve. Right? So when the frequency of the applied force is exactly equal to that of the natural frequency of the body, resonance occurs and the body vibrates with maximum amplitude. When here, in this case, the maximum amplitude, how is it achieved? When the frequency of the applied force is exactly equal to the natural frequency n0 of the body, the body resonance occurs and the body vibrates with maximum amplitude, and the body vibrates with maximum amplitude. So that's your resonance curve. Fine. Now let's try to find out the phase condition for resonance. What will be the phase condition for resonance? Right? Now let's assume that first of all, for resonance you need some external periodic force. When external periodic force is applied to the body, the particle will start vibrating in SHM about its mean position. Right? The amplitude of this vibration will depend upon the natural frequency and the forced frequency. The forced frequency can also be called as the driving frequency. Right? Now, since the forced vibrations in the steady state are simple harmonic motion, the maximum velocity occurs when there's zero displacement. See, I'll show you this. Let's derive this. Let's assume that n is the driving frequency, right? And let us consider that n0 is natural frequency of the body. Now let's consider case 1. Case 1, when the driving frequency is low. When driving frequency is low, that means when n is very small as compared to n0, right? in that case the displacement of the vibrating particle in SHM, the displacement of the vibrating, why vibrating? Because the periodic force is being applied, particle in SHM. Why SHM? Because the body is moving due to restoring force, right? The displacement of the vibrating particle in SHM and the applied force are in phase, right? When n is extremely small as compared to n0, then I can say that the the displacement of the vibrating particle in SHM and the applied force are in phase. Hence, I can say that the velocity will lag the phase. From SHM, we know that velocity is going to lag the phase. Therefore, velocity lags phase, right, behind the applied force by pi by 2, right? That is the extent to which the velocity will lag phase. Therefore, I can say then the maximum velocity approaches, therefore I can say that maximum velocity max velocity approaches 0 max velocity approaches 0 and the amplitude of vibrations is small, right? This is when the driving force frequency is very less. Now let's assume that when the driving frequency is increased from low value, the phase lags the displacement of the vibrating body and the applied force goes on increasing till the time it reaches pi by 2. So let's assume when the driving force is made equal to the natural frequency. When driving force is made, or when the driving frequency, not force, when the driving frequency is made equal to natural frequency, when n becomes equal to n0, right? Now when n becomes equal to n0, this will happen only when the driving frequency is increased by a phase of pi by 2, right? I can say that this is possible. This is possible when driving frequency is increased from a low value when the driving frequency is increased from a low value and goes on increasing till it covers a phase lag of pi by 2 and goes on increasing till it covers a phase lag of pi by 2, right? Now when the driving frequency is made equal to the natural frequency, then I can say that the velocity of the vibrating body will be in phase with the applied force, and say therefore velocity, in this case velocity of the vibrating body will be in phase with the applied force. Once the velocity of the body is in phase with the applied force, due to this the velocity at mean position will be maximum. Therefore velocity velocity at mean position will be maximum, right? If it is maximum, that means the kinetic energy of the forced vibrations varies in the same way as the velocity, hence it too reaches maximum value. I can say that, but kinetic energy of forced vibrations, kinetic energy of the forced vibrations varies in the same way as velocity, varies in the same way as velocity. Therefore, Ke will also be maximum. At this point, the kinetic energy will also be maximum, right? And therefore, the energy, this maximum kinetic energy will be supplied to the body, right? And therefore, the rate of supply of energy of the vibrating body will also become maximum. This energy is supplied to the body, and therefore I can say that the vibrations of the body become maximum. Vibrations of body become maximum, right? That is the reason why you have maximum vibrations when the forced frequency is equal to the natural frequency, and this condition is called as resonance. This condition is called resonance. Fine. Let's consider case 3. When n is greater than n0, when there is a large difference between the applied force and the natural frequency, such that the frequency of the driving frequency is far greater than the natural frequency. In this case, there will be a phase difference. I'll say that the displacement has a phase difference. The displacement has a phase difference of pi radians with the applied force. Right? That means I can say that the phase of the velocity is pi by 2 radians ahead of the applied force. Therefore, phase of velocity is pi by 2 radians ahead of the applied force. Right? Therefore, the amplitude, again when the amplitude and the maximum velocity of the forced vibration therefore become very small. I can say therefore amplitude and maximum velocity of forced vibration are small. So thus you will have maximum amplitude and maximum velocity only when the driving force is equal to the natural frequency. So thus, as the difference between the driving force and the natural frequency goes on decreasing, the phase difference goes on decreasing, and you reach maximum displacement and maximum velocity when the phase difference becomes 0. Fine. The next thing that we have to do is sonometer. Let's consider a sonometer. and this is the length of the sonometer wire. CP, and you have a weight H here, right? This is what sonometer would be. Now sonometer works on the principle of resonance. Let's see the construction of sonometer, right? Construction. A sonometer consists of a rectangular hollow wooden box. Consists of a rectangular hollow wooden box which is called as the resonance box. Called resonance box. Fine. So in which case, one end of the thin uniform metallic wire is rigidly fixed. One end of a thin uniform metallic wire is rigidly fixed, right? And the wire passes over two bridges, A and D. Passes over two bridges, A and B, and finally over a smooth frictionless pulley. Finally over a smooth frictionless pulley. At the other end of the box. That's your construction of the sonometer wire. Right? Now, when the wire is plucked from in between, when the wire is plucked in the middle of the bridges or the stem, it starts vibrating. Right? It starts vibrating with a frequency that depends upon how you're going to plug the wire, with the help of a tuning fork or just simple, right? The waves are reflected from the two bridges, and the length of the wire between the two bridges makes a transverse wave. So if I plug the wire from here, you would have a transverse wave that would be produced, and since the two waves are equal in amplitude and opposite in direction, they produce stationary waves. Fine. The nodes are the two edges of the bridges. The antinode is exactly in between, right? Thus, the length of the wire is nothing but the vibrating length. The length of the wire is nothing but the vibrating length. By changing the length of the wire, the frequency can be varied. Fine, do we get this thing here? So, do we get this sonometer? So, sonometer works on the principle of resonance. Fine. Now let's check with the help of sonometer. You could check the law of length, the law of mass. So most of your laws of vibrating strings can be checked with the help of the sonometer wire. Fine, do we get this thing here? Next, let's start with something else. Mendel's experiment. Mendel's experiment. Mendel is in bio. Okay. Now, he came up with a method to demonstrate that transverse stationary waves can be produced along a string, right? Or what did he do is, he took a tuning fork, he tied a thin string to it. Other end of the string is connected to a pulley and a weight. Right? Now, as the tuning fork vibrates, this will produce vibrations on the string. This will produce vibrations on the string. So what did Mendel do? Mendele's do. Sorry, Mendele's experiment is an excellent method for demonstrating transverse stationary waves along a string. The apparatus consists in the apparatus one end of a string of a uniform radius and density is attached to one of the prongs of the tuning fork, right? And one of the prongs of the tuning fork. The other end of the string passes over a frictionless pulley and carries a light weight. An appropriate tension is applied to the string, right? Now, as the tuning fork vibrates, you have transverse progressive waves that travel along the string and are reflected back. Since I have two waves that are equal in amplitude and traveling in opposite direction, they give rise to stationary waves, right? Thus, stationary waves are set up in the string by properly adjusting the length of, by properly adjusting the vibrating length and the tension on the string. You can have a defined number of loops that can be produced on the string, right? Now, there are two possible arrangements. Either you could do the experiment in this way, that is called as, first this position is called as parallel position, where this would be the length of the string, or this will be my vibrating length. Or I could do the same experiment by changing the position of the tuning fork. Right? That would be another method of doing the experiment where the tuning fork would vibrate and that would set up vibrations in the string. This is my length of the string from here to here, or this is my vibrating length, right? This is called as perpendicular position. Fine, do we get this in clear? Just let's write this down. The apparatus consists of one end of a string of uniform radius, and mass density attached to one of the prongs, of electrically maintained tuning fork. Fine. Now, in this case, I can say that the other end of the string. Is passed over a frictionless pulley. The other end of the string is passed over a frictionless pulley and carries a light weight. Fine. Now, an appropriate tension can be applied to the string by placing weights on the pan. Right? Appropriate tension can be applied on the string by placing weights on the pan. Right? Now, as the tuning fork vibrates, transverse progressive waves travel along the string. As the tuning fork vibrates, transverse progressive waves travel along the string. And are reflected back from the pulley Therefore, I can say this sets up stationary waves in the string. Therefore, stationary waves are set up in the string. Right? Once I have stationary waves set up in the string, by properly adjusting the vibrating length and the tension, on the string, by properly adjusting the vibrating length and the tension on the string, a number of steady and well-defined loops can be obtained along the string. A number of well-defined and a number of steady and well-defined loops can be obtained. So that's how you can get the loops. Now there are two possible arrangements for performing the experiment. One is called as the parallel position. And the second is called as the perpendicular position. Right? Now let's assume that if L is the vibrating length, P is the number of loops, right? Now in that case, if L is the vibrating length and P is the number of loops, then I can say that the length of one loop is going to be nothing but L upon P, total length divided by the total number of loops, right? Let's assume that lambda is the wavelength of the waves. If lambda is the wavelength of the waves, then I can say that the length of the loop should be equal to lambda by 2, right? So in that case, therefore I can say that lambda by 2 is L upon P, in which case I can therefore say that lambda is 2L upon P, right? But frequency I can say that frequency N is V upon lambda, right? So in that case I can say that also V, right in the beginning we said is nothing but square root of T by M. So in that case I can say that frequency is 1 upon lambda into V, 1 upon lambda. Lambda is nothing but 2L upon P. So this will be P upon 2L square root of T by N. So that will be the frequency with which the string would vibrate, right? This is the expression of the frequency of vibration for a string. This is called as the expression for frequency of a vibrating string. Fine. Okay, let's stop this here for the day. Thank you very much.